The next topic is antiderivative. Well, antiderivative is the reverse operation of derivative. Suppose we have a function capital F and then take derivative. Suppose derivative of this is f of x. Then what we are interested in is the reverse operation. For a given function f, we want to find some function whose derivative is the given function. So definition, this capital F is called an antiderivative of small f if this diagram holds. So if derivative of capital F is small f. Let me emphasize this. This is just an antiderivative. Because there are many. We will see there are a lot of antiderivatives even for a single function. Okay, and conventionally we use capital letter F to denote antiderivative of function small f. If you're given small g, capital G will be the antiderivative of the function. So here is one important thing to observe. If you compare two functions ln and ln5x, well, it turns out that those two functions differ by a constant ln5. You can use property of ln to see ln5x is just ln x plus some number. So that's why that explains when you take derivative of two functions, this ln5 will be gone, so two functions share the same derivative. So derivative of f is 1 of x. Of course, the second function also has the same derivative because ln5 will be gone. And actually, you can use any number. Instead of 5, you can use 3, 10, 100, million, and so on. There are infinitely many choices to have the same result. In other words, for any constant, if you compare two functions, f and f plus c, for any constant, two functions share the same derivative. In other words, if you find one antiderivative, then any scalar difference will give you another antiderivative. So is capital F plus c, because derivative of two functions is simply small f. So in that sense, any constant c will give you yet another antiderivative. Geometrically, f plus scalar is the vertical translation. Vertical translation. So say you have a graph of f, then fx plus c is just a vertical shift by c. So you are shifting by c. And this is true for any constant c. So for any function f, any vertical shift will give you the same derivative. So vertical shift will not make any difference in when you take derivative. By c. Okay, here is a theorem. Now that there are infinitely many antiderivatives for a single function, we want to use this capital C to indicate such infinite antiderivatives. In other words, we want to make sure that we have infinite antiderivatives. And using this C, we are indicating that the collection of infinitely many antiderivatives. So if you find one antiderivative, you can use capital C to indicate any vertical shift can be antiderivative. So capital F is an antiderivative, then the most general antiderivative is capital F plus C. So from now, we are going to use capital C to indicate infinitely many such antiderivatives. So don't forget to put this C when you consider general antiderivatives. So we have nice useful table of antiderivative formula. So in the first part, we will discuss some general rule. Number one is antiderivative of scalar multiple is scalar multiple of antiderivative. So C1 and antiderivative of small f. If you want to write the most general antiderivative, you want to put a constant as well. For the second, well, antiderivative of sum is sum of antiderivatives. So f plus g. Well, for each function, you may have c1 and c2, c1 plus c2, but this is yet another constant. You can replace that by single constant. And then number three, well, the power rule says when you take derivative, the power will decrease by 1. When you take reverse operation, the power will increase by 1. So antiderivative of x to the nth power is going to be x to the n plus first power up to some coefficient. So basically, you want to determine some coefficient so that derivative of this is exactly x to the nth. So that's why you want to put n plus 1 in the denominator so that you have canceling. And then once you take derivative, you will get back to x to the n. So that is an antiderivative, and you want to put constant c to get most general antiderivative. Okay, so this is true when n is not negative 1. If your n is negative 1, we have 1 over x. Well, this is derivative of ln, right? ln x. So derivative of ln is 1 over x. That's why this is an antiderivative. For the most general antiderivative, you want to put capital C. Here, one thing to notice is that two functions do not share the same domain. Domain of this is just a positive number, while domain of this 1 over x is entire real numbers but 0. So we want to match the domain of those two functions, and that's why we want to put absolute value symbol. When x is positive, derivative of ln is 1 over x, and it's possible to show that even when x is negative, derivative of this guy is 1 over x. So again, don't forget to put absolute value symbol to have the same domain. E to the x has antiderivative e to the x again, because derivative of e to the x is e to the x. And a to the x, well, exponential function has derivative a to the x again up to some coefficient. So for this, we need a to the x. When you take derivative of this, you will need ln a. That's why you want to put ln a like that. Then you will have canceling to get back to a to the x. Cosine guy, well, derivative of sine is cosine, so we have sine of x and constant. And derivative of this is exactly cosine. For this sine guy, we need cosine. Oh, well, I'm running out of space. Let me write here. Cosine plus c. But derivative of cosine will give you negative. That's why we need negative here. So derivative of that is exactly sine. And then derivative of tangent is secant squared. So we have antiderivative for this function. And then secant has derivative secant tangent. That's why this is the most general antiderivative. For arcsine, arccosine, arctangent, we got those expressions. This is from arcsine. So derivative of arcsine is this function. That's why this is the most general antiderivative. And this is arctangent. And then this is arccosine. So we can use this table to get most general antiderivative for various functions.